Recording in progress.
All right, so yeah, I was only home last week because I needed to take care of some stuff between teaching my other class and between teaching you guys. So, no kitties. I know. Uh, they're a lot more entertaining than I could ever be. So, but anyway, so one of the things we talked about that uh, I was just looking at and then drew a complete brain fart on. Talking about speed limits and safety and stuff like that. So I'm going to flip this over real quick. And if you have the exam one Excel or exam one calculator open, that'll be kind of useful for what we're about to do. Since I need it open, I'm about to do that myself. So let me flip this over real quick. So what ends up happening is, say, Michigan State Police will go to an area and say at a certain speed, or could even say in a certain area, stopping distance needs to be below uh so needs to be below, I'm just going to put some numbers down here and say 130 feet. Now, if we know that, say, at 40 miles an hour, the average car will stop at, say, 120 feet, and we know that the standard deviation for that is going to be, say, 30 feet or something like that. We can use the normal CDF thing to calculate probability of basically all cars will stop, say, before 130 feet. And a lot of times, the way this actually works too is this probability needs to be, say, 95% or higher. So the thought here is just because of the way the world works and the way things are, you can never have it actually be, say, 100% of the time it's a vehicle, or you have to travel at a speed where 100% of all vehicles can stop within this 130 feet. Part of the reason for that is uh, I don't know if it's happened to any of you before, but at one point, driving my mom's really crappy minivan, her brakes went out, which means uh, the only way I was going to be stopping in that thing was either because I'm driving up a hill or if I slam on the parking brake. So if 95% of the vehicles can stop before 130 feet, then the speed limit in whatever this area is will actually be, say, 40 miles an hour. So when we plug all this data into our Excel one or exam one calculator. So let me bring this up. So I said that on average, cars will travel or need, it'll take the average vehicle 120 feet to stop at 40 miles an hour. Said that the standard deviation is actually 30. The We can look at this a couple different ways. The high value here Because we want the vehicles to stop before 130 feet, that's going to be the high value there. Put the low value in there. And you can see right there, based upon the information that we have for this particular area, only 63% of all vehicles will actually be able to stop within the distance that we're allowing. So that means you can't drive 40 miles per hour in whatever this area is because the Michigan State Police has decided that you need to be able to come to a complete stop from speed in under 135 feet, and 95% of the vehicles need to do that. So we can look at the next thing. So let's say at 30 miles per hour, because you're traveling slower, the average is now, let's say, 100 feet to stop. And I'm going to say that the standard deviation is still that same 30%. So now we've come back here, we put in the into the calculator, say 100 feet, and standard deviation is the same. We want to know what percent of vehicles can stop between 0 feet and 130 feet from 30 miles an hour. And this is telling us that it's 84 miles per hour. So let's say we look at one more speed here. So that was 64%. This is now 84%. So let's say we look at 20 miles per hour. And we now know that X bar is going to be, say, you can stop at 80 feet. Let's say the standard deviation here is actually going to be 25 and not 30. So I can now put in here, the average vehicle is going to stop at 80 feet. The standard deviation is going to be 25 feet. And we now have that 95% or greater probability. So this comes out to be 97.7%. So I will stop the share this real quickly so you can see all this stuff. Now I'm going to say that this is based on old cars. With new cars, we can have, but because braking systems are a lot better, cars tend to weigh less, all sorts of stuff like that. Now let's say that at 40 miles per hour, again, in this certain area, vehicles can now stop at say 110 feet and have a standard deviation of, let's say, 25. And we'll do this again at say 30 miles per hour, where we'll have, say, standard deviation, or the average stopping distance is now going to be 90. And let's say the standard deviation now is going to be 20. So these are for new cars. So with that information, I can go back to my exam one calculator. Now I have 110 feet average stopping distance. Standard deviation is 25. You can see right here that only 78.8% of all vehicles can stop at that or at that speed. Now, if I drop this down to say 90, and this is going to be 20, we can now see that, again, 97.7% of all modern vehicles can stop in that safe driving distance at 30 miles per hour. So I know I totally botched it last time, but this is essentially what I'm trying to say. If you're thinking about complaining about how quick vehicles are driving in your neighborhood or say along streets or whatever, if you try to get, say, MSP or whatever other organization it is to come out and try to uh, determine what the speed limit should be in the neighborhood. So again, based on older vehicles, because they all tended to have drum brakes on them, they all tended to be a lot heavier than they are today. And drum brakes are not as good as disc brakes unless you've got some weird situation happening where you've got like $2,000 drum brakes and versus really, really worn out disc brakes based on the old information. And again, these are all numbers that I made up, but we can see that the speed limit should be 20 in whatever this certain area is because we need 95% of all vehicles or more to stop in 130 feet. Now with newer cars, because they have disc brakes, because they tend to be lighter, we actually find that the new speed limit would actually be 30 miles per hour, and we're still going to be able to stop within that, or more, sorry, 97.7% of all people are going to be able to stop within that 130-foot braking distance. So I know for some of you, you might look at the people that are driving down the road in your neighborhood and think, hey, they're going way too fast. Uh, totally get that, totally understand that. But the way that the MSP looks at it, the way that a lot of other cities look at it when it comes time for doing these types of calculations, this is what they're actually doing. They're saying, just as an example, in a residential area, you need to be or traveling at a speed where you can go from whatever speed that is to zero and say, I'm saying here 130 feet. We could put something in there to say you need to be able to stop in 100 feet or whatever the number is, and then go back and actually keep calculating all the stuff over and over and over again until we get a winner. So this would, we could think of this as the old or current speed limits in a neighborhood. If you complain and have them come out and look at it again, this would be the new speed limit. So instead of having cars drive slower through your neighborhood, they could actually say, well, 97.7% of all vehicles are able to stop in this stopping distance at 30 miles an hour. So they will raise the speed limit from 20 to 30 miles per hour, which sounds weird. Well, when you start looking at some of the data like we have here, you get an idea about why it might not be that good of an idea to go and start complaining about uh, cops need to come out and start cracking down on speeders and stuff like that. One of the other really weird things that happens, just out of curiosity, how many of you have ever seen one of those boxes that's like off on the side of the road and you see the two like rubber hoses that are going out in the street? So if you've ever seen those before, what those are there for is to basically measure how many vehicles are driving down that road. Uh, looking at the time between when you go over the first set of hoses and the second set of hoses, they put them a certain distance apart uh, so that they can tell roughly how fast you happen to be traveling. I will say what they're looking at is uh, so if you have the two hoses or whatever that are this far apart, if you're traveling this distance, time between when you hit the first hose here and when you hit the second hose up here, they can calculate how quickly you're driving. And what is literally a really, really weird thing about this is, let's say in a neighborhood or something like that, we do the calculation like this, or like we just did. We find that at a higher speed, people are able, or most people are able to stop their vehicle within a safe drop or safe traveling distance or something like that. And then they look at, say, how many accidents have there been in a neighborhood kind of like yours. Uh, I don't know where any of you live, but how often is there a traffic incident on, say, one of your residential streets? I know I was almost in one a while back, totally my fault, uh, but we didn't have one. So that doesn't go on the record. But what does go on the record is basically all these vehicles are traveling at high rates of speed. There are no accidents, and they can all stop on time, which means if you have someone try to come out and recalculate speed limits, they're probably going to go up, not down. So if your goal is to make the neighborhood safer and have slower speed limits, you should probably actually just keep them where it's at. Does that sound weird to anyone else? And when it comes to speed limits as well, when they go to look at those speed limits, they'll actually look at, like, say, what is the average speed limit through a neighborhood, or what is the average speed limit on a certain road. And if everyone, uh, and essentially, if a lot of people are violating the speed limit and going a lot faster, but they're just as safe as they were before, again, they're going to raise the speed limits. So you can actually have, in some cases, place where, say, the speed limit is 55 miles an hour on a certain stretch of highway or residential road or whatever it is. But because there's so few accidents in there, and they know that people are in general traveling at, say, 65 or 75 miles an hour, and they're doing it safely, you could actually have the speed limit raised from 55 to, say, 65 or 70 because of all the people that are breaking the law. But they are breaking the law, but they're doing it safely. So therefore, maybe the speed limit shouldn't be as low as it is. Totally weird. Literally, people breaking the law set the new standards for the law. Is that weird? Yeah. But is that how it actually works here? Again, yes, it is. Glad I could get through that tonight. Uh, so any questions on that sort of stuff yet?
None that I can think of.
All right. All right. So I'm going to share my screen. At the end of last class period, I started talking a little bit about the exponential distribution. Um, we're going to talk a little bit more about that, but I also want to talk about the Flint water crisis. Uh, oops, don't need that, don't need that, don't need that. Bring this down. So if you're interested in looking at what the actual data is, and there's a web post that we're going to be looking at as well that is very well written, discussing what are the legal what are the ramifications and all that sort of stuff when it comes to the Flint water crisis. You should be able to type in uh, see if I can get it to auto-populate. So Flint water crisis, and then SAS. SAS is a statistical program that I've used in many times. So if I just have Flint water crisis and then SAS, I should be able to hit enter. And the first thing that pops up for me is this quantiles and the Flint water crisis. If you click on here, again, the person that actually wrote this did a really, really good job of dealing with it. They talk a lot about uh, the Flint water crisis and just some of the things that actually went on. Trying to make this so I can actually see it on the screen too. So, April issue of significance, which is a uh, journal or publication that the American Statistical Association puts out, uh, talked about the Flint water crisis and what went on. So there's a link down here to give you an idea about what happened. Um, as far as Wikipedia goes. But you can also look here and you can see that it says the federal lead and copper rule of 1991 specifies a statistical method for determining the concentration of lead in a water supply is too high and actually gets into what that is. And this is saying that if you're dealing with data and the 90th percentile exceeds 15 parts per billion, and this is after you've collected all of your data, then the water is unsafe and action must be taken to correct the problem. When you look at what's happening here, you can see a little bit more about what was going on. And it's you can see here that it says the sample collection process was flawed. Was it flawed? Yes. Was it flawed intentionally? We'll talk about that in a moment. Uh, and you can see that they're actually supposed to grab 100 different samples, but they only were able to obtain 71 of them. And you can see all this stuff. If you have SAS at home, or if you use it for work or some other place like that, you can actually take all this data, copy it, and then paste it into SAS, hit the run button, and it's going to work. The data that we have right here is the actual factual data that was collected while all these people, or while the people were out collecting water samples, and these are the concentrations that they found. And you can see here, when they do the analysis, they found that the 90th percentile, the concentration for the 90th percentile is 18 ppb. Up here, it says anything above 15 ppb tells you that you have issues and you need to go back and rework the problem. And you can see down here, somewhere in here, uh, sorry, when you look through all this stuff, and from a statistics point of view, this is a very accurate, number one. Two, it's written for people and students like you who might only be learning about statistics in the first place. But one of the things that they get into is that a couple of the samples that were collected were actually thrown out for various reasons. And we're actually going to get into that. What happened was if you throw out those values or those concentrations, all of a sudden the 90th percentile goes from being 18, which tells whoever's analyzing the data, hey, you need to take care of this. You need to be looking at this. Uh, it's now coming in below 15, which means the water is safe. And you can see, like down here, they ended up getting rid of the highest concentration. And when you look at the data that they have here, you can see the two samples that were actually excluded from everything. And if you notice, we're gonna try to reproduce this graph when we do, it's gonna look a little bit better than what we've got here. But you notice that around 0, we've got this high value. And then as we go out further and further and further, it gets lower and lower and lower, which is essentially what an exponential distribution should actually look like. And one of the things that happened with this particular data, so again, there's a sample out here of 104. There's a sample back here that were both excluded. This 104 sample was actually excluded, and we'll get to it in a moment. Uh, but basically because if you were to take a class in what's called analytical chemistry, one of the things that they teach you in that class is that data should be normally distributed. They also teach you that when you're talking about concentration data, like we have here, that should also be normally distributed. And that there's a procedure that they actually teach you in there where it tells you whether or not you should actually delete a particular case because it's considered an outlier. So in order to do everything and to show you all the stuff that's going on, I have to do some really boring stuff, but I'm actually going to do it in front of you. So I can highlight the data in here and I can actually copy that. I'm going to bring it into Excel. I'm going to bring it into a new sheet in Excel, and I am going to paste it. And the way that this is set up right now, there's not much that I can do with it. So I need to go to, I believe it's data. And there's a thing up here that says text to column. This is what I want to use. I'm going to use what's called delimited. I'm going to click down on next. And because there's a whole bunch of spaces here that I want to get rid of, I'm going to click on space and then click next. So if you can see off on the left hand side here, all of these zeros that are in green are all in one cell, and Excel is treating that not as a whole bunch of zeros, but essentially as a word. We want to treat it as data and numbers. So I do all this stuff, click next, click finish, and now I've got all of this data set up. So now I can look at all of this and I can copy, and I'll try to drag this up a little bit. I'm just going to come over here and paste it, but I'm going to do a paste special, and there's something called transpose. So transpose, it's a fancy term that you find in uh, like linear algebra and stuff like that. But basically, if I have a row of data and I want to transpose it, I turn it into a column of data. If I have a column of data and I transpose it, it's going to turn into a row. To make my life easier, I need all of my data to be in a column. Right now, this is in 4 rows, so I have to go in and transpose all of this data literally by hand, exactly the way that I'm doing it right now, right in front of you. So I'm just paste and transpose, paste and transpose, paste and transpose. Oops, I didn't want to do that. I wanted to transpose it. Geez, sometimes you get a bit ahead of yourself. Sometimes you just have to deal with the nonsense of Excel as well. So I know all of this is essentially boring as all get out. Totally understand. But once I've got this done, so I'm going to transpose that. I can now get rid of all of this data here. I'm actually going to delete and shift cells up. Uh, so I'm going to say this is the original data. I'm also going to try to make this a little bit bigger so all of you can see what's going on. And I know that I'm going a little bit fast with this, but if I'm honest about it, the material that we're covering in here and what we're doing isn't even supposed to be part of the class. But because it is dealing with public health data, this is a public health program and all that, I am actually including it. So I've got the original data. And I'm just going to type here uh, average, oops, and then standard deviation. That should be an equal sign there. So now I can come up here and I can type in equal to AVG, or AV, and they're uh, typing out everything for average. So I'm going to come in here and I'm going to highlight all of the data that I've got. And I'm going to close the parentheses. And you can see that on average, uh, 7.334 ppb is the average here. Going to look at the standard deviation. So this is St. Diva. Again, I'm going to highlight everything that's on here. And I'm going to close the parentheses. And I now have my average and my standard deviation for this particular data set. If we look at what they were talking about here, so talking about the 90th percentile, uh, question that you should have is what is an actual percentile? There are actually two different definitions where if you listen to them, they sound almost exactly the same, but they are in fact not the same. But has anyone ever been told that, say, their exam score or something like that was in a certain percentile? So, like, if you took the ACTs or SATs, the score that you had, sorry, when you took them, placed you in, say, the 70th percentile or 90th percentile or anything like that. Is anyone familiar with that type of terminology?
Yeah.
Okay. So when it comes to percentile, there are actually, like I said, two different definitions or two different ways of dealing with it. And they are both technically correct. They both give you fairly similar values, but they're not always going to give you exactly the same one. So one of the definitions, and it, if you think about it for a little bit, you're going to be like, hey, these are the same thing, aren't they? But when you start looking at certain types of data, you realize uh, it's probably not actually the same thing. Well, with one of these, so let's say we're talking about the 90th percentile. Couple different ways we can define this. We can define the 90th percentile as the concentration. So we saw all that stuff that was in the table. What is the concentration where uh, when you stop and look or stop at that particular value, 10% of the data is greater than it. Not 10% plus 90% is 100%. So the 90th percentile is either 10% of the data is larger than it, or when you're looking at the data. So if you can think about it, and let's say I sorted the data highest to lowest, and we think about this as say you're going in an elevator and you're going to the 90th percentile floor or something like that. Definition one would be 10% of the floors are above you. Definition number two would be 90% of the floors are beneath you. If I have a lot of data, the difference between those two definitions is honestly minimal. Uh, if we're looking at smaller data sets like what we've got here with the Flint water crisis, that definition could actually be considerably different. So when we talk about, say, you scored in the 90th percentile on the SATs, one, congratulations on that. But two, does that mean 10% of the people that took the test are better than you? Or does that mean you are better than 90% of all the other people? You basically have to look at how they define it, how they calculated it to get the idea behind it. What we're looking at, though, is more, say, what I would have been told to do in, say, my analytical chemistry class. So let's get back to that part. So I'm going to go back to sharing the screen. So this is dealing with the percentiles. If we go back and we look at the data that I've got here, we can look at this data, and essentially what we're going to do is we can take these values, and I'm going to write them down really quickly. Original data, we've got X bar is 7.34 ppb, so that is parts per billion. Standard deviation is 14.41. And kind of like we did with the trying to figure out what is the speed limit going to be in this particular area, we're looking for, say, 95% of all the data or of all the people driving cars to be able to stop in under the certain safe distance. We can take the same idea here, and if you look at all the data, you can see that we've got a couple 43s, and then kind of out of nowhere is 104. So what I'm going to ask here is, what is the probability of getting a value based, if I assume that the data we have here comes from the normal distribution, what is the probability that this 104 data point is actually true? To do that, I can go to my normal distribution here. I'm going to put in the average that I have. So 7.34. My standard deviation is 14.41. The low value I want here, because I want 100 ppb and above, my low value is 100. My high value, I can make it say 10,000. And you can see, based upon the data that we have here, and I'm writing something down off screen and I will show you what it is in a moment. So this is 6.4 E negative 11. What is that trying to tell us? So if I flip this over. So quite literally, again, based upon the data, if I assume a normal, and this is all stuff that I was literally taught to do in my analytical chemistry class. what is the probability that we would get a data point that has 100 ppb of lead or greater, comes out to be this value here. This value is written in scientific notation for those of you that don't remember scientific notation, or you all know scientific notation, right? Totally? Okay. So what's going on here is the probability, again, based upon the data I have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh, and just so we know, e to the negative 9 is 1 in a billion. So e to the negative 11 is basically 1 in 100 billion. And that's kind of where we're at with this. So between 1 in 10 billion and 1 in 100 billion. So I do expect an answer from all of you on this one. Oops, wrong one. If there is a 1 in a billion chance or a 1 in a 10 billion chance that that 104 data point actually belongs in our data, do you think it's a real data point, or do you think it's maybe someone screwed up something somewhere? We might not be able to trace back the mistake, but just because of how high the concentration is, it's kind of telling us that there's a 1 in, say, 10 billion chance it would actually occur. So if there's a 1 in 10 billion chance that it's real, do you think that it's real, or do you think that it's fake? Or maybe not fake, but say a mistake, something that should not be part of the analysis that we're trying to do. So error, mistake. How many of you think that it's an error or a mistake? And if you want to like do the little hands up emoji or whatever, I'm totally fine with that. Okay. So when the scientists saw that, that is literally one of the reasons why they got rid of that data point. If they assume that the data is normally distributed, based upon the assumption that the data is normally distributed, that high concentration has a 1 in 10 billion to 1 in 100 billion chance of actually belonging. Because the probability was so small, they thought, just like all of you did, it must be a mistake. Uh, Problem is, the mistake that occurred was on their belief that the data is actually normally distributed. So I'm going to go back to my Excel spreadsheet real quick. Uh, so again, I'm trying to get this so that I can actually see what's going on, but sometimes the Zoom screens kind of get in front of me. So where did I put that? All right, so sheet number 2. Going to drag this and put it at the end. Now, if I want to create a histogram of the data so I can get an idea of what type of shape the data looks like, I can actually come up here, highlight everything. Then I can click on Insert. And up here, there's the thing that says Insert Statistics Chart. And I want a box plot. I'm going to drag this up slowly but surely. I hate how Excel won't just like automatically put this uh, at the top where we kind of want all this stuff to be. So again, if we have a normal distribution, or we would have low on the outside and it would come up and make like a bell, or it's called a bell-shaped curve. Does this look like it's a bell-shaped curve at all? And the number of bins that they have here is actually a little bit deceiving. So I can, oops, click on the uh, x-axis here. Now I'm going to change the number of bins from 9, let's say, to 11 and see how that looks. So that helped out a little bit. And click on here again. Let's say I change it to 21 bins. So this is actually looking a little bit better, like I'm expecting. Looking at the graph that we have here, does that look like it's bell-shaped? Or does it look like it starts high on one end and then slopes down and eventually creeps down to 0? Who thinks it's bell-shaped? Who thinks it starts high on one end and then kind of like a ski slope uh, goes down to nothing? So because of the way that the data looks, to me, this actually looks like it's either exponentially distributed, or I would think that it could be what's called log normal distributed. If this data was exponentially distributed, these two values here would be approximately the same value. So if I had an average of 10 and a standard deviation of 12 or something like that, I'd say, okay, that's close enough. But looking at the data that I've got here, it looks like the standard deviation is about 2 times what the average is. To me, because I've done these calculations many, many times before, I can go and create uh, I can go and create a confidence interval for the standard deviation, and it's not going to come anywhere close to the 7.3 that we have here. So that's telling me that it's not only different from what we'd expect in a uh, exponential distribution, but that it's actually quite a bit bigger than that. So in order to do this, I need to come in and I need to transform the data. So I'm going to look at this, or I'm going to say this is the original data. And I'm going to try to get this kind of off the screen here for a moment. And what I'm going to do is I'm going to basically take the log of all the data that I've got here. So the log transform of the data. To do that, I have to type in equal to log. I've got a lot of different types of logs I can choose here. I'm just going to go with the log base 10 that most of us are actually familiar with. So log 10, close the parentheses there and then hit enter. We have something interesting pop up here, but I'm actually going, well, let me do it. I'm actually going to drag this down all the way. And what you can see is that when I take the log base 10 of all of these, I end up getting a different value. So I need to get rid of that. So you see that all of these have a value of log base 10 of 1 ends up being 0. But all of these zeros up here, we've got this hashtag num exclamation point. That's the calculator trying to tell me, hey, you idiot, you just screwed up. You can't take the log of 0. So what I have to do here is something kind of weird, and it is something we're going to talk a little bit about either tonight if not tonight, and most definitely in our next class period. I can do something called run a simulation. So what I'm going to do is for all of these values, and when you look at the concentrations here, you see how they're all nice integer values. If any of you have ever worked in a chemistry lab before, you know that uh, you're supposed to have a certain number of decimal points with all of your calculations, blah, blah, blah. And these are all rounded to integers. So what happened here is all the values, they went out, and let's just say, for instance, looking at these values here, where it actually comes up as 1, they are actually not a concentration of 1 ppb. They just happen to round to the value of 1. So they could be 0.5 to 1.4999999 all the way out. And when we round them, they'll round to 1. For these, they all rounded to 0, so I know that the concentration is somewhere between 0 and essentially 4.99. So I'm going to create some random values to put in here that will actually give me a value between 0 and 4.99. To do that, and to do the simulation, I have to type into here equal to rand and then between 0 and 499. And whatever number is randomly generated, I'm going to divide that by 1000. And when I take these numbers and drag them down, you can see a couple of things here. So even though this one is 0.494 and the one above it is 0.425, they both round down to 0 and not up to 1. So I know that I did this calculation correctly. If I said 0 to 499 and then divided by 100, what's going to happen is all these values are going to be essentially between 0 and 4.99. So I had to do it divided by 1000 just to get what I need here. And now I'm going to take the log of this new value that I've got here. And one of the things that's going to happen is every time I do a calculation here, the numbers over here are in fact going to change. It's just how this stuff works out. Fortunately, though, I can come over here, copy paste all of this over here. And what I've got now is that the log or the average value from the original data after I take the log is 4.2297. The standard deviation for that is now 0.7015, blah, blah, blah. If I make it redo calculations literally by, say, typing a 1 here, you can see that roughly the average stays between, say, 0.4 and 0.45. The standard deviation stays right around 0.7. So 0.7 to zero point 0.8, maybe a little bit below, maybe a little bit above. But what I'm going to do now is say X bar is 0.45, let's say. And the standard deviation that I'm going to look at is, let's say, 0.75. And now, because I'm dealing with log, I want to know what is the probability. So you can see the log of 104 here is actually 2.017. I want to look at what is the log of 100. So the log of 100 is actually going to be 2. So now based upon this data, looking at what is the probability that I will get a value uh, through random chance uh, with an X value of 2 or greater. And I know that this is a lot. And like I said, this is not something that you guys actually need to know about in your class or for this class. It's just something where, since it is the Flint water crisis, I figure it's something that's kind of important to do. So the low value here is going to be a 2. The high value again can be whatever we want. And this is now telling us that there is about a 2% chance that when you look at the data and you analyze it properly, analyze it the way that it should have been analyzed, that sample that's at 104 on the regular scale, on the log scale above a 2, actually does belong to the data set. So now, based on what we just did here, and I know this was long-winded and all that sort of stuff, but what we've actually done is analyze the Flint water data that was collected. We recognize the fact that the data is not normally distributed. So the analyses that a lot of the scientists did originally is not valid. So when they decided that because there's a 1 in 10 billion to 1 in 100 billion chance that this data point or that 104 ppb data point does not belong, uh, and they got rid of it, we're now saying if we do a proper analysis of the data, there's about a 2% chance that thing actually belongs. And I'm going to stop the share real quick and flip the camera over here. So we saw that this was about 2%. So how many samples out of everything that we had should we expect to get? So that's where this expected value comes from. So it's P of X times N. P of X is going to be this 2%. N is going to be these 71 samples. 0.02 times 71 or 71. What do you get when you do that? So, so based on our proper analysis of the data, we're actually coming out here and saying we probably should have gotten 1.4 samples that were 100 or greater. How many did we actually get? We actually got one sample that was above 100. This is saying we should get a 1.4 or greater. So if we got 0 in our data set, can we rule things out or say that it's not what we expect? I would expect, uh, just because of, again, I've done these types of calculations before. With these 70 data points that we had, I would expect to get somewhere between, say, 0 and 4 samples that are above there. Maybe 0 to 3 samples that are above there because of where that number is. And we got 1, which is what we would expect. So when you think about all the stuff that happened with the Flint water crisis, had the scientists done the analysis properly, had they looked at the data, and instead of assuming that the data comes from a normal distribution, which we see it clearly does not come from a normal distribution, and they did the analysis the way that I just showed all of you, they should have expected one to two of their samples to be that high, which means when they saw it, they should not have thrown it out. Had they not thrown those out, you can go back and look at the blog post that was in there. That's going to make the higher concentrations still relevant, still in the sample. That's going to push the 90th percentile for the data over uh, 15 ppb, which would mean that the people of Flint, sad to say it, they still would have been poisoned, but it would have been for, say, 3 months instead of the year or two when before uh, the children at Hurley Medical Center were actually coming in and testing or having significantly higher lead or blood lead levels than they had previously. So again, the people of Flint, they still would have been poisoned, but it would have been for, say, 3 months instead of 15 months or 2 years or however long the Flint water crisis went on for. Uh, so if you had the choice of being poisoned for 3 months or 2 years, I think we would all choose 3 months. Ideally, we wouldn't want to be poisoned at all, but unfortunately, the way that we have to do these things sometimes, you make a change the way that they did. And then you go and you look at the data. And if you look at the data properly, you can see, hey, we expect there to be some of these really, really high concentrations. So when you see it, don't think it does not belong. Think that it does belong and keep it. So I think I'm done with my Flint rant, but there is actually one other thing to talk about. And when I'm done with this, we will take like a 10-minute break. And if any of you have questions about some of the previous homework, we can work on that. And because I've got to draw stuff, I might not see anything if you put it into a chat box. So if you do have a question, feel free to unmute yourself and ask the question. So if you read what they did when they were collecting the water samples, you they are in the Flint or in that SAS thing. They just came out and said there were some issues with the collecting water samples, and essentially there were. And what I'm trying to do here is I horrible drawer. Most of you probably know that already. But I'm saying let's pretend like this is what the city of Flint looks like. I know it's not what the city of Flint actually looks like, but in Oakland County where I live, this is what Sterling Heights looks like. This is what Warren looks like. This is what Roseville looks like. Troy, Canton, Plymouth, blah, 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 Rochester, Rochester Hills, these really big squares. For the sampling plan, there are actually a couple different types of sampling plans that they could have used. So I am, of course, pretending that both of these are the same size and the same awesomeness as far as squares go. We can use something called random sampling. And I'm going to do a couple of these just so we can see what would happen. And what they wanted to do originally is go out and collect 100 samples. If they use completely random sampling and they're going to go throughout the neighborhood, basically what they're going to do is they're just going to pick a bunch of points at random and pick 100 of them. And then wherever my pen came down, that is going to be a house that they actually go and talk with the homeowner and get a water sample from them. looking at it the way that I just did it here, that looks like pretty good coverage of the entire city. One of the downsides is from random sampling, I can have it happen something like that. Then if you notice, there isn't any sampling done that's up in this upper part here. To prevent issues like that, I will say this is completely random sampling. And I'm going to say by taking the city and breaking it down into, say, 9 groups like this. And again, I know that Flint doesn't look like this, but hopefully you get the idea of what I'm trying to go for here. If I use what's called stratified random sampling, I can look in each one of these groups, and then I will now pick 9 samples roughly at random in each one of these particular boxes. Okay. I know that they're supposed to have 100. And when you look at this, you're going to say, well, that's 99. So you pick one extra spot, one place, or something like that. This is a much better idea. Should any of you happen to be going out for whatever job you have in the future, if you are going to be collecting samples from, say, the public for whatever reason, using the stratified randomly or random sampling is a much better idea. Um, so if you happen to, or if any of you start working for a public health department a in some county somewhere, or if you happen to be working as a public health nurse and you need to go out and collect samples, and I've actually met some of the nurses that do this, collect out samples to see what are the prevailing STDs that happen to be in the population of people of Detroit. Uh, totally sad stories about that, and how I know about all that stuff. But anyway, being able to send out someone into, say, those 9 quadrants, and then you randomly grab, say, 10 or 12 homes from each one of them. That makes sure that you get full coverage of the entire city. Couple of the downsides of doing it the way that I just showed. What happens if one of those quadrants is almost totally and completely, say, commercial buildings or industrial? So if we're talking about Flint, one entire section like that could actually be, say, the GM plant that's between Flint and Flint Township. If that's the case, there are no homes there. You mark that entire quadrant off, and then you do more sampling in the other places that are still available. A couple, from a statistical theory point of view, what you do once you've decided to do this stratified random sampling is you pick, say, 10 homes at random, and then you go into all 10 of those homes, no matter what. Person at the front door telling you to get off their porch with a shotgun in their hand pointing at you, you say, sorry, statistics says I need to come in there, so you're going to have to walk out of or move out of my way, homeowner. Does that sound like a good plan to anyone? So when you do this, the way the way that it actually works in reality is you will have, say, I am supposed to sample 123 Maple Lane, and then you walk up to the door at 123 Maple Lane, and then you try to talk with the homeowner. If they tell you to get the F off their porch, sorry for disturbing you. My apologies. Have a glorious rest of your day, and then you walk away. s- some of the things that happen in reality, especially in parts of Flint or say Detroit, which is where I actually got to do a lot of this stuff. Uh, you might choose 123 Maple Lane, but then when you go to that house, uh, so one thing that can happen is the homeowner is not there, so you can't talk with the homeowner. Two, the person that is at that home, they might be home, but they are not the homeowner. They are just renting the home. So you might need to contact their landlord to get permission to come in to grab the sample. And let's be honest, uh, if you're a landlord and you've got a bunch of older homes in, say, a really bad area, a rough area of Flint or rough area of Detroit, do you really want someone coming in and testing the water in one of your homes for lead? Because all of that information will become public knowledge. So do you want the public to be able to look up a home that you own and see what the lead concentration is? If the lead concentration is zero, it's a great selling point for you as the home or the landlord. You can say, hey, rent this place. We have proof there is no lead in the water. Here's the official government document showing that it's true. But if you do have lead in the water, uh, sucks to be you. So you can have these issues where the the landlord does not want you coming in. They are the owner of the home. They have final say, so you can't do anything about it. Number three, how many of you have driven through a neighborhood and found that there are a whole bunch of abandoned homes? That's an issue that we had when I was going through Detroit. And sometimes they were abandoned homes, but they were still in, say, good condition. Could we have, say, gone into these homes and perhaps found that the water was still running to the house and collected water from the kitchen sink? Maybe. What are some other issues that we ran into? Uh, I can't say anything about Flint, but I will say in Detroit, when we were scouting some of these homes, basically what we had to do is pull up in a non-nice vehicle because we are in a kind of a rundown neighborhood. So if we pull in, uh, drive-ins, like say someone rented a BMW or a Mercedes, we'd really stick out. So we had to drive a really crappy vehicle into the neighborhood and just sit there and wait and check out the home and see what's going on with it. Because some of these abandoned homes that we wanted to use were actually drug dens. And you could watch as there's a lookout on the corner. They're looking around. A car would pull up. That lookout would kind of look around, make sure everything was cool, walk up to the car, and have a little bit of a transaction with whoever the driver was, walk to the abandoned house, knock on the door, put money through like the door or whatever, grab something, walk back out. Here you go, sir. Here you go, ma'am. Have a great day. And then the car drives off. So do we want to be trying to knock on the door of a drug dealer's den? Absolutely not. So there are a lot of ways where statistics says we have to go to 123 Maple Lane, but because I like me, I don't want to die for my job. We have to come up with other ways of doing this, which is why I suggest that if you are going to be doing something like this, you break the area you're going to be testing or looking at down into, say, 10 equal size blocks. You try to make sure that all the blocks that you're looking at have essentially the same number of homes in them. And then even though you need, in the case of what I was showing, 9 samples per block, and then you need one more on top of that from wherever. Choose 15 different homes, choose 20 different homes. That way, Once you've got your 10 or 11 samples from that particular area, you've collected enough samples, you're done. Every place that you went to was randomly selected, and then now you can go about your day. One of the other things that happens if or can happen is if you routinely go to a certain area to do these types of water testing, a lot of times whoever it is will be told, oh, you have to go and get a house that's on, say, this block or on this street. Well, if you've been there before many times, you might know that a certain person on the street will always happy to let you in and test their water. Well, if you're always testing the same house over and over and over again, that's actually going to be violating a couple of the other assumptions for the data that we are looking at. If you tested their water once and it was contaminated with lead, chances are every time you go back, it's also going to be contaminated with lead. If there was no lead in that particular house, chances are you'll never find any lead in that house. But does that particular house not having lead, or does that particular house having lead in the water mean that all the other houses on that block are exactly the same? No. And if you look into the some of the news reports and look at what has been done to help the people of Flint, they are trying to replace the lead lines that go from the main sewer line into the house. One of the issues they had is what? They don't know where all these lead lines are at. So the best they can do is say, well, we think there are a bunch of places in this neighborhood that have it and a bunch of places over here that have it. We're not sure about the rest of these. So let's go look at these. Let's go do an intense lead screening in these neighborhoods. If we find high concentrations of lead in the tap water in these houses here, then we will assume that it's the lead line that's coming in from the water main, and then we're going to replace that. And one of the things that they found was those lead lines, they aren't very good. And they were put in, say, 120 years ago. So there are some of the homes that already had that removed. So when they would go and test, there's no lead in the water, or there might be, say, one ppb in the water. And as we were or looking on there, 15 and above is a reason to be worried. So one ppb, is it lead? Yes. Is lead dangerous? Yes. But it's at such a small concentration, it's not going to be all that harmful unless you happen to be highly sensitive to it. All right. So that is the complete Flint water crisis rant that I have. Let's take 10 minutes and we'll start talking about, or I'll try to finish up with the exponential distribution so that you can actually do one of the homeworks. And I really, really wish I could head out of this office and go grab a bottle of water right now, but I don't think I'd actually be back in time. So if any of you have any questions about the homework, feel free to ask.
Um, I believe I understand. I'm almost, I just have to revise like one more thing for the homework that's due today, the journal rather. But, um, I guess just so I make sure that I am looking at how to do, next week's homework correctly. We're using the calculator and
Well, which homework is due next week? Is
the
that
book three, the airplane one.
okay? So the airplane and the second part of it is using. So the first part you can use the exam one calculator. For the second part where you're dealing with uh, people or shoppers at the grocery store and all that, That's actually going to be the multiple uh thing that I was showing last or a couple weeks ago. I will say the multiple thing does not work very well on Mac computers, and it does not work very well if you're using Microsoft Excel online. So if you have Office downloaded and running on your laptop, that's where it's going to work out best. And that's part of the reason why I suggest that a lot of you actually work together on it. Not because I not or it's literally because some of you might know what you're doing, but you might not be able to do it on your computer. Okay. So make sure you're using Excel on a Windows computer. If you do that Lab Anywhere thing, you will be able to do it that way. However, the further away you are from campus, the slower the mouse clicks will be, which can make it very frustrating, but you can still do it. And to answer one of the questions a lot of you had about the first part of the homework, we are using the binomial distribution. And like I said, when we were talking about it, what was it, 2 weeks ago, or whenever it was, with the binomial distribution, you have a probability the event is going to happen, and then you also have to have a maximum value. So the question here is, what is the maximum number of tickets that are sold? Not the maximum number of people that are on you can get on an airplane, but what are the maximum number of tickets that are sold? And then what you're looking for is how many of those people are what is the probability that you are going to bump someone from an airline flight. If you don't know what bumping someone means, it just basically means they overbook the flight. So literally, I don't remember, honestly, I don't remember the numbers that I gave you all. But let's say I said that there were 160 tickets that are sold, but the plane handles 150 people. If 151 people show up for the flight, either someone in there is not going to be able to get on or make it on that flight. So that's would be called bumping the passenger. So in the case of you sell 160 tickets and you have 150 people on the flight, the probability that you're going to bump someone is that binomial distribution for 160 people or binomial CDF 160 people minus binomial CDF of 150 people. And like I said, I honestly don't remember what numbers I gave. And I've been using the same homework thing for what, 6, 7 years. So I should probably remember what the numbers are, but I'm way too lazy for that.
For the airplane, it is 120 seats. They sell 130 seats, and they know that 85% of the ticket holders show up on average.
So, like I said, if it was 160 tickets sold and 150 people show up, uh, the probability that you're going to bump someone, and I will do this one, or I'll do the problem that I'm talking about, because the whole point of homework is to make sure you can do the homework problem. So if I come on here and hate some of the stuff that just pops up all over the place, get out of the way. Oh, God, stupid thing. Um, Right, so I'm going to create my own problem here. So I said there are 160 tickets that are sold, and instead of 85, let's say we know that 87% of the people will show up. And now what I'm interested in is what is, if there are 150 seats on the plane, my high value here is going to be 160. My low value here is going to be 150. And this value that I have right here is the probability that or the airline is going to have to bump someone because they don't have enough seats. And when you look at the value that I've got there, we can round this and call it 0.002. So 0.2% of the time, based on the problem that I just came up with, uh, you're going to have to bump someone. You're going to have to like physically remove someone from the airplane because uh, you don't uh, you don't have enough seats for everyone. Does that sound so if you are the airline, assuming that you don't have to bump anyone, you are literally making 10 seats worth of just pure profit. Because if they don't show up, you keep the money and you don't have to provide any type of service. And if you remember several years ago, there were some issues with people getting dragged off of planes and people are kicking and screaming and stuff like that. And this is actually kind of where that problem comes from, or the problem that I'm asking you is kind of based on that. The numbers I'm giving you are totally made up, but we have 0.2% of the time someone is going to get bumped off the plane. And if we have a certain number of flights going back and forth, back and forth, back and forth. So let's say an airline has, or this is true for all the airlines, uh, routes and all that. And let's say they have 10,000 flights per year. So the probability that they're going to bump someone is this value. The number of people we would expect them to bump in a year is equal to probability times the number of flights they have. So I'm just going to say 10,000 here. So what this is saying is that among all 10,000 flights that this airline has, there's going to be 19 flights where they bump someone. 19 flights out of 10,000. So if you think about it, uh, 19 times a year, someone gets bumped. That sounds horrible, but it's 19 times out of 10,000. So it's really rare, and it's rare like cancer rare, or certain types of cancer rare, but because there are just so many of these flights, it's going to happen all the time. And if it happens 19 or 20 times a year, or even if we say it happens 24 times a year, let's say, that means that once every 2 weeks, someone is going to get bumped from the air or from their seat. So once every 2 weeks, you can see another viral uh, thing of someone being dragged off of an airplane because they've been bumped. Does that mean that the airline is necessarily bad people or anything like that for doing it? That's for you to decide. But it also gets into some issues that if any of you have studied psychology before, uh, you uh, you can look at certain things and you see that it happens. In this case, again, if there were 24 flights where it's bumped, you see that it happens every other week. So you're going to build up in your mind that this is a really common thing. This is a really big problem. But the only reason it happens essentially every other week or every 3 weeks is because there's so many chances for it to happen. So did I just way overdo every single question that was in part one of that homework?
No, I appreciate it, and will, I think I understand it a lot more now. Thank you. Now, follow-up question. I have a Mac computer and I use the Excel calculator from that, but I
Mhm.
haven't like downloaded on my computer as like an app. Now, is that different than what you were talking about where we're gonna have trouble with it?
Okay. So let's see if I'm still logged in. Of course I'm not. So anyway, if you go on Canvas, and I'm gonna share my entire screen again. So if you go in on Canvas, there is this exam one calculator that should work, whether it should work online, it should work on a Mac, it definitely will work on Windows, it should work on Linux. If you have the Excel app, and let's say you only have a tablet that's running Android, the Excel one or the exam one calculator should work for you.
Okay, perfect.
However, go for it.
I haven't had any issues so far, so I hope that's a good sign.
Okay. So the thing where people in the past have had issues, uh, especially if they're using a Mac, is using this multiple file. Because one of the things that's going on here is in the background, there is literally a computer program that is running. Um, I used to know how to actually show you what the computer script looks like. For Mac, uh, some of them do not like to run that script at all, no matter what you do. Uh, if you're using Windows and when that pops up, it'll probably give you there's a security concern with this file because of that script that was in there. The file that I gave to all of you is the file that I use. There shouldn't be any issues with it. If you are concerned about that, I totally understand. The option you then have is to go to, so U of M Flint, and then I believe it's the My Portal thing. Go to this Lab Anywhere thing, and then connect via this web client here. And then when the security concern comes up, you are literally using a computer on campus. So if there is a virus on it, it's not going to affect your laptop. It's going to affect a laptop or it's going to affect a computer that's in a computer lab here on campus. So you're going to be totally safe. Might be issues for Flint IT department, but Flint IT department, they get paid to take care of that stuff. Let them work it out, right? So that is the other option. So if there is an issue, or if you have, for whatever reason, like let's say you're using a laptop that you got from work and you have to have extra security protocols and stuff like that. Again, U of M Flint.edu, Lab Anywhere, log into it, log into a computer that's on campus, and then through, say, Google Chrome, through Safari screen, through Microsoft Edge, whatever you happen to use. You can then log into um, the computer on campus and use that computer on campus and treat that as your home screen. And then you can do all this homework as well. Okay.
Okay, thank you.
All right. So let's get back to the exponential distribution. There's actually just two formulas that we need to really understand to be able to work with here. So what's happening with the exponential distribution? We talked about it a little bit last time. So we can have something at a really initial starting point, and then we can have it do something like that where it just slopes down really, really, really quickly. We can have something else where it slopes down, but it doesn't slope down anywhere near as quickly. And then at a certain point, it just continues on and on and on and on forever. It never actually gets down to zero, but after a certain point, it's going to be 0.000000000 or whatever. So effectively, it's nothing. With the calculations that we do, if if I want to look at it, and let's say I am looking at uh, amount of time, and this is say number of things that are working. I can use the equation P broken. And because I don't know what work any of you are going to be doing in the future, we can think of this as being broken. Or if we are doing a toxicology test or experiment, we can think of this as the probability something is going to die. This is going to be equal to 1 minus E. And then the notation here is really, really weird, but it's mu divided by negative x. This mu here is the average. The x value on the top is whatever your value of interest is. One of the ways we can tell that we're going to be dealing with whether or not something breaks, another word for average when it comes to this is mean time to failure. So if any of you have ever used a or like say put together a computer at home, one of the things you have to put in there are case fans to circulate air. Those case fans will all say something on them like mean time to failure, 10,000 hours of use. Okay. The X on the top is we want to try to figure out, or one of the ways that we can use this is we might want to try to figure out uh, how often do we need to say replace a case fan? A lot of different applications that we can talk about here as well. Uh, to put it into more of a public health or a health kind of an idea, we can look at, say, batteries that go into people's pacemakers. Every time you need to replace that battery, you have to give the person another surgery, pull out the old battery, attach the new battery, stitch them back up, and hope that what, one, the battery actually works. Two, hope that the patient doesn't or didn't just get an infection. Three, you're probably going to have to put them under some fairly heavy sedation in order to do all of this stuff. So there are all the risks of a major surgery every time you need to do this. So you might ask a question like, given how long this battery lasts, or the average time this battery lasts, so the mean time to failure, what batteries should we be using so that less than, say, 10% of them fail in 5 years? So that is a legitimate concern and a legitimate question to ask using these types of calculations. If you, I know in the past I've had some students, maybe none of you that are watching this live right now are part of this, but if you're, any of you are part of the health information technology or health information systems program, some of the things you would need to worry about are how long do the hard drives run on the servers that you're using at your place of business? So you need to ask questions like, uh, how often should we be replacing the hard drives in our servers, given that the manufacturer says the mean time to failure is going to be, so if it's in hard drives, it's read-write operations. Really weird thing to think about for this. But basically, you can think about it if you're not familiar with it, like say you go to library and how long is a book going to last? And it's based on how many times it's checked out. So there might be a mean time to failure for, say, a book that's 20 checkouts. So how often should you be reordering that textbook or reordering that book uh, so that you don't have any issues with, say, the book just completely breaking and falling apart on you? So you can always have essentially an up and running, fully functioning hard drive on your servers. So doctors, if you're, because this is going to be at a hospital, so that the doctors have access to all the patient information. You don't lose any of the information and you don't have any unplanned, or you minimize unplanned or unscheduled work. So you can come in and say, 2 in the morning, swap all these drives out, have them ready by say 4 in the morning, so that any doctor that's coming in at 5 in the morning or later, or when they do a shift change, it's not going to affect the majority of people. So we can look at it in terms like that. Uh, and when we think about it as well, because we are, the formula that I showed you is the probability it's going to be broken by a certain time. The opposite side of that is what's the probability it's still going to be alive? And what happens with this is there's another couple different distributions that are actually similar to the exponential. They are a little bit more complicated. This exponential distribution is already beyond what we're supposed to be covering in here. But because of the use in the Flint water crisis, because of the use uh, for legitimate students or for students that are legitimately taking this class, I include it anyways. It's also useful in toxicology. But what we can ask, or some of the things we can do as well, are say things like, if the average life of an animal is, say, 3 years, what's the probability they will live to be 10 years or more? Uh, we can do that calculation, but it's going to be basically one minus the probability the animal dies within the first 10 years, just because of how things are set up here. If I want to ask, what is the probability that's, again, say this animal dies between, say, 6 and 8 years? again, we can use the Excel or the exam one calculator to do this. And it's literally the difference between what's the probability it dies in 8 years minus the probability it dies in 6 years. That's the probability it lives to be 6 to 8 years old. Okay. So a lot of useful stuff here. I'm going to share my Excel calculator. So if we look at the EXP distribution, so again, if I want to know, or if I say that on average an animal lives to be 3 years old, what is the probability it'll live to be between 6 and 8 years old? And that is the probability right there. I know talking about animal deaths is a horrible thing, uh, but we can look at these sorts of things. And I think we were talking about my cats last time. If the average cat lives to be 7 years old, what is the probability that they live, like I was saying, my brother's cat, who I helped take care of for many years of that cat's life, uh, my mom's cats. My mom passed away 11 years ago, and one of her cats just passed away like 6 months ago at the age of 18. So, what is the probability that a cat is going to live to be 16 years or over? So, based on the average life expectancy of a cat, or the mean time to death, in this case, mean time to failure, is 7 years. We should expect approximately 10% of all cats to live to be or live to be between 16 and 10,000 years old, based on the calculation I've got here. Okay. So, a lot of legitimate uses that we've got here. If I wanted to say between 12 and 16 years, that's only going to be, as you can see here, 7.8%. So some of the things we can do with this, if we needed to, we could look at, say, uh, 0 to 4 years. So that that is the probability that a cat will die within its first 4 years of age. I know this is depressing. 4 to 8 years, that's the probability it will die in that time period. 8 to 12 years, that's the probability it'll die in that time period. 12 to 16 years, there we go. 16 to, oops, not 30, let's say 20 years of age. That's the probability that a cat will pass away in that time period as well. So we can go back and we can look at these and we can try to figure out what's actually, or am I, like, say, am I doing something special where uh 6 out of the last 9 cats I had all lived to be over the age of 15 or over the age of 16 or something like that. Is that something special that I'm doing? Do I have some sort of a magic touch, or what's going on? And you can see that we expect 10% of cats to make it that long anyways. So it, depending on how you look at this, um, that could be a thing where if you're thinking about adopting a pet, but you're or say giving your, at one point we were looking at giving my grandmother a dog because she's home alone, and she's hard of hearing, so having a dog could be really beneficial for her. If someone comes and knocks on the door, she's probably not going to be able to hear it. But then the question is, what's the probability that the dog is actually going to outlive my grandmother? So we have to do a calculation like this. which is just weird to try to do. It's awkward, totally understand that. Uh, when I was working with a toxicologist, as a toxicologist, we had to do calculations like this, unfortunately. Uh, Getting back to what I've got here. So a lot of this is actually used in something that in biostatistics is called survival analysis. So we can have, let's say, two different things that we're looking at. We've got one thing that's like this. We've got another thing that's starting at the same point, but the slope is a lot more gentle. So it's kind of like this. I'm going to call this condition A, and this is going to be condition B. For both of these, let's say probability that something's going to break under condition A is going to be 1 minus the exponential mu under condition A uh, to the negative x. What is the probability that something is going to break under condition B? That's going to be equal to 1 minus E mu, or the mean time to failure, mean time to breaking for product B minus, so I'm going to say XA and XB. So one of the things that we want to try to do here, or one of the things that we did with toxicology, was we're looking at what is the difference between these two things. So we're trying to figure out what is the difference between these two things, and is there a statistically significant difference? And just looking at what we have here, whoever gets condition B here lives longer. So again, this isn't something that we need to be all that worried about for most of you anyway. However, having an understanding of, uh, again, this is survival analysis. We're asking under which of these conditions is better if we assume that living longer is a better thing. So if you're a mechanic or something like that, you could say, well, this is how long the engine's going to last when you use conventional oil versus, say, really good synthetic oil or something like that. And then you can do a cost comparison to see, should you be using that synthetic oil, which costs more every time you change your oil, but if it allows your vehicle to last 300,000 miles versus 70,000 miles, is it worth it? To me, because I'm going to be driving the same vehicle basically until it breaks, I'm going to be using synthetic oil over conventional. If you're leasing a car and you're going to be turning it in anyways, I would probably go with conventional because you're not going to be owning the vehicle later on anyway. So if it does break after 70,000 miles, it's not your problem, right? Your lease is over at, say, 40,000 miles or 50,000 miles or whatever it is. So we do have those options. There is one more thing that we need to look at here. So I'm just going to write this as the probability of an event occurring. So 1 minus E negative X over mu. So I believe one of the calculations you need to do is try to figure out what these values of X really are. And because you all so totally remember abso-freaking-lutely everything from Algebra 2, and it's all top of the mind. Uh, we know that you can solve this to give you the x value. I have to give you a probability. I have to give you mean time to failure, and then we can calculate this. And just as a reminder, to do that, I want to isolate what I've got here. So I've got to take this 1, put it on the other side. So that's going to be p minus 1 equals negative e to the negative x over mu. Because I've got the negative here, multiply everything by negative 1. That's going to give me 1 minus p equals e to the negative x over mu. Because I've got the exponential here, we got to do the opposite of the exponential, which is going to be take the natural log. So now I have the natural log of a 1 minus p equals negative x over mu. So if I want to get x by itself, I have to multiply both sides by mu. And because the negative here, this is actually going to be negative mu. So I'll have negative mu equals the natural log of 1 minus p gives us x. So with this, the way that I've just written it here, so getting back to what I said originally about um, if we're looking at how long do we, or how often do we need to replace a battery, or what type of battery should we get? Or sorry, if we have a certain battery, how long should we leave it in the patient? Again, assuming we only want 5% of these things to break while they're, or stop functioning while they're in the patient. This is the amount of time we can actually let it go. So if we have, say, uh, let's think about this in days. So let's say we're told that the battery has a mean time to failure of 10,000 days. 1 minus, and I said 5% is the cutoff we're looking for. We can calculate how often we should go in and replace this. 1 minus 0.05 is going to be 0.95. So if I go to share my screen again. So if I go to just any type of a calculator, doesn't need to be a graphing calculator, just needs to be scientific. So you can actually do this calculation on your cell phone. You just might have to turn it sideways. If you have a graphing calculator to do this, that is awesome as well. And I've got negative 10,000 times the natural log of 0.95, close parentheses. And that right there, so the 512.9, so 513 is essentially how often we should be scheduling this patient to have the battery replaced in their pacemaker, if we're talking about batteries in a pacemaker. If we're talking about hard drives in the servers that some of you might actually use, again, we could say once every 500 days or so, you need to go in, create a backup of whatever hard drive it is that you're going to replace, and then replace it. And you can go about your business that way. We can also look at this in terms of uh, if we think, well, 513 days is too often for this. So again, if we're talking about major surgery to do these, maybe we should look at a battery that has a mean time to failure instead of 10,000 days, let's say 20,000 days, times natural log 0.95, close parentheses. And by essentially by doubling the mean time to failure, we just essentially doubled how often or the amount of time between surgeries. So a lot of different stuff that you can do with this. And the thing that I've got you doing is very similar to this, but we're looking at it under a whole bunch of different conditions. I think I've actually got you. I'm going to stop the share real quick. So coming back to what we've got here, I'm going to write this on another sheet of paper. So I've got natural log of 1 minus p equals negative x over mu. If I want to figure out, let's say I buy a bunch of these products and I want to try to figure out what is the mean time to failure for them, I can rewrite this as my estimate for the mean time to failure. It's going to be negative x divided by natural log of 1 minus p. So I can actually go back and do the back calculation to see about how long these things actually last. And a lot of times too, with the toxicology experiments, this is more the type of thing that we're interested in because this gives us a calculation or an idea of how long someone's going to live or how much shorter someone's life expectancy is going to be based on certain conditions. So I know some of this was actually quite a bit morbid, but uh, with this exponential stuff, so like we were talking about last time, you can use the exponential distribution to try to figure out how much of a concentration of a medication is in someone's blood and actually calculate it out specifically for that person. So you don't have the issues like we were talking about where all the medications that you take are generally based on a 160 to 180 pound man. Since most of you in this class are not a 160 to 180 pound man, it might be nice to make sure that when you go to the hospital, you get the right dosage for you as opposed to the dosage based on something that you're completely not. Um, see what else. So it's, we've got what about another half hour, and I honestly don't know if I want to start talking about the next thing or maybe just save it till next week. So how many of you are done mentally?
I raised my hand. It's been a long week.
Okay. Anyone else done today? So either a lot of you are already so out of it that you don't even know what I'm asking, which means you're done, or you've already passed out, so you don't even hear any of this. So yeah, so I'm going to end it at this. Next week, we will talk about a lot of different applications of everything that we've done. Uh, I will say the simulation thing that I was showing you, that can actually be a pretty cool thing to use because there will be some times when you have a question about something, but you don't know exactly how to try to calculate it. You can either spend many hours days, weeks, months, years trying to learn how to make that calculation properly, or spend 20 minutes, do a simulation, and get an answer that's a whole lot or almost as good and doesn't take you anywhere near as much time. One of the things I used to have my students calculate was essentially uh, if since this was for a business school, what is the probability that a vehicle is going to come in under what's called a lemon law because of a certain part? And I said, let's assume that the mean time to failure for this part is 60,000 miles and the warranty on the vehicle is 100,000. So what's the probability that the same part is going to break 3 times in under 100,000 miles? Going to be honest, I don't even know how to calculate that. And I've asked ChatGPT and some other things to show me how to do that. And I look at the answer and go, what? I've talked with other people that actually do these calculations. They don't know how to do it. Why? We use a simulation. So we can get a PhD in statistics to answer one stupid question, or he can spend 5 minutes doing something and get the correct answer or get a close enough answer. So that'll be for next time. And I also get to update one of my stories about one of my friends when it comes to something called decision analysis. So cool. Talk to you all next week.
I actually have one
If you
question.
have any idea. I'm sorry.
Sorry, I just wanted to get you before. I just have a quick question, but you can.
Sure.
Um, so for the second part of the assignment, homework three, that is also using the subbinomial calculator, correct? Or
Part, the airplane part is using the exam one calculator.
okay,
The second part of that homework is using that multiple file.
okay, okay.
So, in I'm gonna share my screen again. I don't need that. Do I still have the multiple? No, I've got that. I'm not gonna save anything there. And open up the multiple file, blah, 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 blah. So not gonna go through all of these with you, but just really quickly, for one of the problems on there, we're looking at an arrival rate, I believe, of what is it, 100 customers?
Yes, 100 customers.
What is the service rate for a particular cashier?
I don't, let me pull it up.
Okay. So, and I will say, with this homework problem, you're probably, or a lot of you are probably looking at it and like, why are we talking about cashiers at a grocery store? I'm getting a job or I'm getting an education so I don't have to be a cashier at a grocery store. But quite literally, the same types of rules, same types of thoughts and ideas apply. So even if you are a nurse, if you are a respiratory technician, if you're, I think we did one of these talking about one of your classmates is going for her, uh, what is it, a
Physical therapy?
doctorate of physical therapy. So how can we help her plan how many physical therapists or say physical therapy assistants she needs to have hired in order to make her the most amount of money? It's all based on this stuff. So anyway, Brooke, did you look that up?
Yeah, the It says customers do not want to wait more than 10 minutes in line. So would that be the
Mhm.
rate?
Well,
It says
how
customer rate
many,
anywhere from the one column says there's 100 and then 12 cashiers, and then on the other side it says 120 customer rate to 14 cashiers.
yeah. So somewhere on there, it should say something like the average cashier can handle however many customers per hour.
Oh, 9 customers per hour. Okay, I'm sorry.
Okay, no problem. So this is all new terminology, new everything. So the cashiers can handle 9 customers per hour. There are 100 uh, customers coming in per hour. How many cashiers do we need to have running? And did I tell you anything about uh, the waiting cost per customer?
I don't recall learning about it prior, but let's see what the waiting time is. 10
Not
they
waiting time, but waiting cost.
oh, waiting costs. Okay, so the in both cases the grocery store loses revenue, and they estimate the cost of waiting to be $5 per customer waiting, assuming the cashier cost is $15 an hour and can handle 9 customers per hour.
Okay, so I'm gonna, just because I'm trying to make get this in as close as possible, I'm gonna rewrite this as cost up here. I'm gonna just say here, this is equal to whatever value I have down here. So again, if your classmate is looking at uh, how much money or how to minimize cost for that facility that she's going to open once she graduates, this is again the type of calculation that she needs to be doing. So the number of servers I've got here, you've got to change that. So I think based on the data I gave you, first number was 12, right?
Um, yes, 12 cashiers to a rate of 100.
Okay. So with 12 cashiers that can handle 9 customers per hour, that cost the grocery store $280.86 per hour. And we said that the customer wants to spend, let's see, uh, so the average time for the customer, did I say waiting in line or just in the system?
Okay. The customers are unwilling to wait more than 10 minutes in line. Once the line gets this long, customers leave their items on the floor. New customers won't bother coming in. In both cases, the grocery store loses revenue, and they
Mm.
estimate the cost of waiting to be $5.
So, so again, if you're going to be sitting there waiting, or if it's going to take you more than 10 minutes to get through the line, let's say. So if we think about it that way, get through the line, this is the value that we want, or this is the value that we're interested in. And you can see up here, if we only have 12 cashiers, that is the cost of that this place incurs, and people wait 12 minutes. I change this to 13 cashiers, you can see the amount of time they spend in the system. So this means from the time they get in line till the time they're handed, say, the receipt at the end of their transaction is now 8.4 minutes. And what happened to the cost here? What was it under 12? So it costs you $280 or $281 per hour, and you have a bunch of angry customers. I change that to 13, you have a lot fewer angry customers and your cost actually went down. If I change this to 14, you can see that the cost went back up again. So pretending, again, you have to put in the real numbers, but let's pretend that this is your classmate and she is trying to figure out how many uh, physical therapy assistants she needs to say prep the patients that she's going to get for whatever, or if she's going to be starting a clinic, how many physical therapists does she need to have hired at the clinic in order to, say, maximize revenue or minimize cost or whatever it is. So she'd need to put in the actual cost per hour for all of these. And then you can go through these and see. So 12 cashiers, $281. 13 cashiers, $265. 14 cashiers, $271. So under this particular, uh, the values that we have in here, the optimal solution here is to have 13 cashiers. You put more on, can you get more customers through? Yes, but it's going to cost you a little bit more money. If you only have 12 cashiers on there, uh, can you can you function like that? The answer is, of course, yes. But you're going to have a lot of pissed off customers because no one likes waiting in line, right?
Yeah. And
So, go ahead.
oh, I'm sorry. I was agreeing. Nobody likes to wait in line, even when it's a
Yeah,
self-checkout.
yeah, yeah. So, places like Meyer and Walmart have actually started using these types of calculations to figure out, is it more financially beneficial to them to, say, have one cashier watching six self-checkouts, or to have, say, six cashiers running things, self-checkout, because every person's doing it, it's going to be a little bit slower per customer. But because you only have one cashier watching six people at a time, the cost is significantly smaller. And because you have the six people going at a time, it can actually be quite a bit faster. Another place where this sort of thing pops up, there's an electronics store by my house where sooner or later I'm probably going to be spending $3,000 to $4,000 to buy a new computer. Don't tell anyone that I know that. Um, but what they do is everyone gets in the one line, and then as a cash register opens up, the next person in that line goes in. The lines can be phenomenally long, but because they'll have eight cashiers, even if you're 24th person in line, again, because of this sort of thing, you might wait 8 minutes. 23 people ahead of you, 8 minute wait. It's a beautiful thing. So, uh, and again, if you want to put these into real terms, for, say, in ER versus how many nurses do you need to have? How many respiratory therapists do you need to have? That sort of thing. You can put the numbers in for real and actually figure out literally what is the optimal solution if your goal is to minimize cost. And what you're going to find here is that quite literally, the optimal solution is essentially always going to be put more people on than you think, but not a whole lot more than you think. So if I, in pretty much everything that we just did here is three answers that you can all put on your, use for your homework. So make sure you watch this video again, later. gonna flip over the camera real quick. But with all of these, the thing that ends up happening is I make a graph. There are two different ways that these graphs could actually go. We'll say cost and then versus the number of workers. A lot of times what's going to happen is you're going to start up here, it's going to go down, and then it's going to go back up again. Because if you are a business owner, you want to save money, you want to minimize cost. So this is how many workers you're going to need. Depending on the system that you're dealing with, depending on how many or how much money, say, a cashier costs, or how much money that physical therapist costs, or physical therapy assistant cost, or whatever, versus how much money you make per customer, you may end up with something that looks like this, which means this is going to be the number of workers, and that's going to be the minimal cost that you have here. So depending on what goes on, how much you're paying, how much you're losing by having customers go to other hospitals, other physical therapy places, stuff like that, you might find that you only need one person. If you have more than one person on, your costs skyrocket. Other times, like what you're going to find with everything you do, at the smallest value, it's going to be high, it's going to come down at a certain value, and then it's going to go back up again. So based on what we just looked at, that's 12, that's 13. So that's 12 right there, that's 13, and we'll say that's 14. So how many cashiers do you want under that first set of conditions? You want 13. Does that work?
Yes.
And so those are literally some of the answers. And again, whatever popped up, those are the answers I am looking for. So I just did 3 of your homework problems for you.
Thank you. And I really appreciate it because now I understand practical value and
Yeah,
behind the numbers, not just plugging them into the
yeah.
calculator. Thank you.
Yeah, like I said, I actually had an interview at a hospital that's closer to my house, and I was trying to show them this, and the people that I was interviewing with refused to admit that anyone would go to any of the other hospitals in the area. And and if we're talking about a ER, and someone has a legitimate emergency, you're dying from a heart attack, you're dying from a car crash, and you're squirting blood all over the place. You don't have a choice where you're going to go. You're going to the closest hospital possible. End of discussion. I understand that. But for the rest of us, if you have the choice of, say, going to a hospital that's going to treat you like crap, assume that no matter what, you're coming to us, so we don't even need to try, versus the hospital that wants your business. They've got extra people on staff so that they can get you either in and out of the ER, in and out discharged, or in out and say admitted to the hospital and get it done in say 2 hours versus 9 hours. Where are you going to go? I don't think there's a choice there.
Yeah, but close.
So that's all the stuff I'm trying to get in or talk with you all about, because I know at some point some of you will be in the situation where hospital wants to cut costs and they're going to want to cut staff. You all now have some method for saying, hey, wait a minute. Let's look at these numbers for really real. Let's see what happens. And then you make all the accountants go, I never learned about that. Like, well, tough. This is straight out of business stats. And if you don't know it, then you didn't go to good school for business stats. So, or whatever. But anyway, any other questions?
None that I can think of right now. But
Okay.
thank you so much. And we hope you have a safe drive and you get some water. And thank you.
Um, I'm definitely leaving here to go grab some liquid. Probably not water. It's going to contain some water, somewhere between 90 and 95% water anyway.
Good.
So, anyway, have a good evening. Torture you guys next week. And Johnny, do you have any questions or were you just hanging out or are you already passed out?
Oh no, I was just kind of hanging out while I was going over my homework.
Okay. So do you have any questions?
Nope, not so far. I think I'm just gonna
Okay.
do
All
another watch through and
right.
dig through.
All right. Cool.
Hey, wait, do you want to see
Well,
my cat? Since here, hold on. I never share my screen, but here you go. He's meowing. Okay, can you see?
oops. Well, almost. Looks
Yeah.
like it's really dark in your
Yeah,
bedroom or wherever.
I'm in the living room and it is dark. But yeah, I just wanted to show you. I know it gets dark so early now, but thank you.
Yeah. See you later.